Okay, shall we start?
Yes,
I can
please.
see
I think
more
so.
and more students are coming. Okay. Hello, everyone. Good morning and good evening. This is Xichang Wu from Southeast University. Welcome to the Urban Lifeline Public Seminar Series. And today we are very honored to invite Professor Hao Zhou from the University of South Florida to give a speech on the topic of from assessing to improving lane keeping assist in production vehicles, data collection, empirical analysis, and generative artificial intelligence enhancement. Dr. Zhou is an assistant professor in the Department of Civil and Environmental Engineering at the University of South Florida. His research focuses on traffic flow theory, connected and automated vehicles, and cyber-physical transportation engineering. By leveraging open source platforms like OpenPilot, Dr. Zhou bridges the gap between theoretical model and deployable transportation technologies through hands-on development and deployment. He received his PhD degree in civil engineering from the Georgia Institute of Technology, where his dissertation focused on traffic flow aware control strategies for autonomous vehicles. He also holds master degree and bachelor degree in transportation engineering from our Southeast University. This seminar will last for around 1 hour, including a 15 minutes Q&A session after Dr. Zhou's presentation. And so without further ado, let's welcome Dr. Zhou to give the presentation. And Dr. Zhou, you may start when you're ready. Thank you.
Thank you, Dr. Wu, for the nice introduction. Yeah, actually, I don't think I need one since I spent 7 years at SEU. It feels like coming back home. So, yeah, so I'm a guy working on traffic flow research. Probably you're not quite familiar with this background. I graduated from transportation engineering at SEU. I spent a lot of studying how to design roads, how to knew a little bit about pavement engineering, and I learned quite a lot from the 7 years at SEU, which helped me a lot, helped me to navigate through my PhD at Georgia Tech. And more recently, I moved to Tampa, Florida, and work at University of South Florida. So I'm a big fan of production vehicles, so which are the real cars moving on the road. So I'm particularly interested in studying the impact of real cars on the road on mobility, either on safety or traffic efficiency. So today, I'm going to share some of my work on the impact of production vehicles on safety part. So today's focus will be on lane keeping assist. So without further ado, let's get started. Let me share my screen here. And feel free to record the session if you haven't started. Okay, there we go. So what is lane keeping assist? So lane keeping assist is a very popular, prevalent safety feature in today's vehicles. So I guess many of you are not unfamiliar with it. So it's a function basically helps you center your car within the lane. It can automatically steer in your steering wheel and to keep you out of the to prevent you from drifting out of the lane. Of course, lane keeping assist, or we call LKA, is marketed as a catalyst for safety. It is advertised by the car companies, and it's such a great feature, and you can leave everything to it. But in reality, it's not that good, or it might actually does more harm than good. So existing LKA problems. If you ever used or tried LKA, you will quickly notice or agree with me that LKA system can disengage very frequently without a good notice, or sometimes even it keeps it engaged, it may drift out of its lane unexpectedly. So especially when you meet in challenging weather or lighting conditions or geometry conditions such as sharp curves. But if you don't have good land markings, like the examples shown on this slide, it does not really perform well in heavy rain or when you encounter a sharp curve, as this GIF shows. It can drift out of the lane, posing a great safety threat. And if your lane lines are worn out, it does not detect those lane markings very well. And sometimes in winter weather, you have snow-covered lane lines which cause occlusion, which also pose a lot of challenges for the lane detection of the LKA technologies. There are a few research gaps that motivate our work. I think the fundamental issue we'll try to address here is to investigate LKA's safety impact, whether it is safety function or not, or does it really improve or degrade current safety of the roads, especially those lane keeping or lane departure crashes. Do they contribute to them, or do they try to reduce or lower the crash rates as they are advertised by the car companies? Okay, so what are the research gaps around this problem? So first, we don't really have a lot of granular data for the LK products. The main issue of this lack of data set is that those LK systems, they are black boxes by OEM. So you purchase the car, you get the lane keeping assist function, but you never know the details. And it's designed to be proprietary. You control stacks, you never get access to the algorithms, and you can never access the data. So currently what you can do is just experience and let it steer in your car. It can do a lot of dangerous things, but you have no control about it, and we don't really understand it. So the first gap is lack of granular data. So the second gap is that those three gaps are intertwined. So due to the lack of data, we cannot have empirical performance analysis, and we don't really understand the impact on safety. We cannot come up with good strategies to improve the readiness of our infrastructure for those autonomous driving technologies. And as from the driver perspective, since the LKA is basically a black box and it's a complex vision-based opaque black box, it creates a lot of challenges for human drivers to oversight or to use the system. And out of concern and out of the frequent disengagement you might encounter in real life, many drivers may end up not using the technology. So I guess that's the truth. So many of us, our cars are equipped with technology, but since we don't really understand when this technology is going to perform or not perform, so it most likely we will end up not using the technologies. So here are the three major gaps around the current LK technologies: the lack of granular data, the lack of empirical analysis, and the challenges for human drivers to oversight this black box. And this whole research is motivated and designed to address these three gaps. Okay, so we have three preprint papers on arXiv. So the first one is to address the gap one, empirical data. So we release an open data set of lane keeping. So we managed to reverse engineer the data from production vehicles, and we solved the challenge of current challenge of the lack of raw source data from production vehicles. Using those empirical data, we are able to conduct a detailed performance evaluation, which leads us to the second paper, Empirical Performance Evaluation of Land Keeping Assist on Molded Production Vehicles. And as mentioned earlier, so it is very challenging, cognitive challenging, and very demanding for human to oversight a black box, especially complex, vision-based, and imperfect black box. So to assist the human drivers to oversight this system to bridge the gap between human oversight and the black box driver assistance system, we proposed a vision language-based model to predict LKA failure to alert human drivers 2 or 3 seconds before the incident will happen. So human drivers can rest assured knowing before when LKA would fail, so they can gain more confidence or feel more comfortable in using these technologies. So that will be the whole storyline of this series of research, also today's talk. Okay, let's jump into gap 1. LKA ground truths from production vehicles is still missing. And the underlying reason is that all LKA systems from those OEMs, they are black boxes. So we cannot directly read or understand the internal messages from the systems. So due to this impediment, here is the state of the art. So studies either use external measurement. For example, in figure A, some researchers have put an external camera and mounted it on dash cam. And here you even use the sunglasses to try to prevent a strong light. And or they are using, by the way, so if you put those cameras, you can still, you cannot access the internal signals of your LKA system. So, and many researchers are using non-production vehicles. Some of them will use the vehicles in their lab, or some of them even go for simulation. And more recently, in last year, the Department of Transportation in Texas, United States, they conduct some road experiments, but unfortunately, they were not able to conduct a very comprehensive study. The tested scenarios are quite limited. And here we go, we try to address those research gaps in the limitations in current study. It is a comparison of our dataset OpenLKA with existing other dataset of autonomous driving. So our dataset OpenLKA is the first large-scale dataset specifically designed to collect real-world performance of lane-keeping assisted system from production vehicles. Among all other datasets, they are mostly used for perception planning and other tasks. So they often lack specific performance evaluation metrics. And the most distinctive feature of our dataset is that we get all the data from production vehicles, the real cars running on the road. We are not using any high-end autonomous driving cars coming out of the research lab. So by contrast, we test the car that you might actually drive. So we test the exactly the same system you might use on your road in real driving scenarios. Okay, so this is our OpenLKA website. You're welcome to check out the website. And on the left, we show the we sketch the setup. So this is where you sit in your car, and this is your front windshield. and we mount a phone-like device here, which is actually Comma 3X. So this is basically an Android phone running aftermarket LKA system. But note that we are not we are only using it for data collection. We are not overriding any LK commands of the OEM system. So this small device, our data collection tool, it also pulls the data out of the OBD2 port interface. So OBD2 port is what car mechanics use. So if you go to a car shop, you want to remove a red light signal of your car, probably your engine light. So you'll have a mechanical come by. So they will most likely bring out a device called CAN logger, and they plug it into your vehicle so they can read and they know what's going on in your car. They can also help you fix the car, and they can also help you to remove that wrong engine light. So here we are doing things in a similar way. So we use a device connected to a car, and we read all the logs from your car control network, which is known as CAN logs. And then we decode those logs to get LKA data. This is a framework for our data collection and performance evaluation. On the left side, we start with building an LKA dataset, and in this case, we have conducted a lot of target experiments in Tampa, Florida. So in Tampa, it rains a lot, and the sunlight is very bright. So we have very challenging road conditions here. But of course, we don't have winter weather conditions here. As mentioned earlier, we use CAN logs and to get the raw internal data from the vehicles. It includes kinematics, like the speed or steering angle. It also includes the torque, the steering torque, and most importantly, it actually contains some LK internal messages, like that if the lane line has been detected, what is the status of the lane line, and based on that, we are able to know if the lane line detection is working properly. And we use this phone-like device. We call it a dash camera, since the main purpose of this device is to capture from the road scene, to get synchronized video. So the CAN logger only tells you the car status, but it does not tell you what's going on the road. So we need a synchronized dash camera. So with this dash camera, it also makes generative AI technology possible. So to extract, to understand what's going on the road. So this would not be possible before the era of generative AI, but now, previously you can get the dashcam video. You can probably get the speed of the other vehicles, you get the lane lines, but you don't understand the whole traffic scenario, the road scenario, the weather conditions. But now with vision large language models, with proper prompting, it can detect and understand very well the line marking condition, the weather condition, the lighting, and if there are some crossing pedestrians. So there are three pillars here on the in the LK dataset. We have CAN logger to get internal signal from the vehicles. We have dash cam to capture synchronized video, and we use vision large language model to get rich context out of the videos. So that's the pipeline of the data collection. And we do include a lot of different car brands, Volkswagen, Tesla, of course, Honda, Toyota, the two popular car brands in the US market. And you might ask, how can we get so many cars? And the answer is that we get the cars from the airport. We use rental vehicles. So by renting those cars, we get exactly what most customers would drive on the road, and we are able to extend our fleet from 1 or 2 lab vehicles to dozens of vehicles in a very financially feasible way. Okay, so that's mainly about the data collection. So with the internal car messages, the video data, and the vision large language model annotations, we are able to do a lot of empirical analysis, so which I will introduce shortly. And we also come up with a lot of practical advice for infrastructure management. So if you're working in the transportation sector, so geometry design is probably one of the major tasks of the daily job. So here, how can we improve our road geometry design to make it more ready for autonomous driving, autonomous vehicles for LK technology? And we will have that answer for you. And for normal, for the transportation agencies, if you want to increase road safety to prevent the lane departures, what you can do is you send those preemptive warning system advisory informations to your drivers. So, but that will rely on connectivity information. But it's good to know if your where your infrastructure is going to fail a lot of current LKA systems on the road. So that is the framework of the data collection and performance evaluation study. Yeah, we have talked about this, the data collection. Just a quick recap, it includes mainstream car makes, and the data set include detailed CAN messages, synchronized dash cam videos, and VOM annotations. And beyond that, we acknowledge that our group cannot get all kinds of vehicles on the road, and due to our location, we are located at Tampa, Florida. So we are in a subtropical climate and geological location. So how can we get other weather conditions? How can we get other more challenging geology and more challenging weather condition, lighting conditions? So we will integrate a lot of open source community data. So which we will introduce right now. So in this figure, those circles, it shows where we incorporate the worldwide LK data from other countries. So we pull out this data from Comma community. So Comma AI is a company that share that our testing devices. Some people around there are about more than 5,000 active users of this service around the world. So when they drive, use their own production vehicles in their own country in different weather and different road conditions, they're sending the data back to Comma Cloud. And many of those data, they're open sourced, they're public. So our data set integrated those open data. So we create a so-called ecosystem, which is continuously growing. And by integrating community data, our data set scales in an unprecedented way. So we are able to include about 389 hours of LK driving, and it's distributed all over the world, covering different road conditions, weather conditions, different production vehicles. So yeah, with that being said, in our target experiments is consists of about 260 hours of LK experiments in Tampa, Florida. And from community, we get naturalistic driving of around 80 hours from the Kama community. In Tampa, Florida, our experiments include various road conditions ranging from highway and two-lane rural roads. This is our experimental rental cars we got from the airport. And on the left, we show some images we got during the data collection process. And on the right, we see different major car brands on the US market. This is the experimental setup. As mentioned earlier, we have a phone-like device mounted on the dashcam window, and we activate the lane keeping assist on those production vehicles, and we use it to get the CAN data, the videos, and based upon that, we use VLM to get rich context out of the videos. And it's worth mentioning that this device, it actually runs a parallel lane keeping assist system, which is more sophisticated and developed by Kama AI community. So we use their lane detection as a proxy of the ground truth. So otherwise, it will be very costly to measure where the true lane lines is. So possible ways is you can install LiDAR on top of the vehicle, but that will be very costly and very hard to scale. So Kama AI's lane detection algorithm has been proven to work very well by millions of hours of driving data. So it's a reliable lane line detection technology, and based on their lane line detection, we are able to estimate the lateral position of our vehicle. So based on that, we would know the lane deviation accordingly. Here are some targeted testing scenarios. So we try to cover as many as challenging scenarios we can get in this Tampa area. So to name you a few, we have starter lane lines, heavy rain, and glaring lighting conditions. We have faded lane line, nightly driving, and to investigate the impact of road geometry, we have road transition areas. For example, here, there is a fork of the road. So one road is split into two lanes, and we have sharp turns. And we also noted that sometimes traffic condition can be a big influencer. So if you're in congestion traffic, the lane lines might be occluded. So we include a lot of very congested scenarios to investigate that. After we get in the data, we reverse engineering using the open DBC files. They are also public files. They help us to decipher the signals from most production vehicles. And when those DBC files are not available, we also did our own reverse engineering work to find the key LK relevant metrics. For example, we try to, this table shows that we can get the steering angle, the lane detection results, and if this LK system is engaged or not. Let's talk about our VLM annotations. We're using ChatGPT 4.0. We basically send the frames to OpenAI's API, and our prompt is to annotate a road image using the designed rubrics we send to them. So here is our table. This is the prompt we send to ChatGPT. We want a generative AI to label those conditions in the using the table we shared here. Okay, so this is prompting. As you can see, we describe how we actually categorize a weather condition or lighting condition. We give ChatGPT very detailed instructions and structured this instructions. We also improve the prompting after many iterations. Try to get good accuracy out of it. So this would be an example. We send 3 consecutive frames: previous frame, current frame, and next frame. We have a task description, instructions as role prompting. We also added some chain of thoughts reasoning to help generative AI to better label, categorize those road conditions. And here is an example of the output. It can output the landmarking, which category it falls into, and it also provides explanations. So we evaluated our annotation results. We compare it with our manually sampling checks, and the overall annotation accuracy is pretty high. And ChatGPT 4.0, even if it's not the most advanced VLM in the world, it does a very good job, but it's also very expensive. So we didn't send a lot of images, but it cost us like thousands of dollars to finish the annotation task. Okay, so the summary about of the OpenLKA, it is the first of its kind open dataset of lane keeping assist function from production vehicles. It includes about 400 hours of driving, including target experiments and naturalistic driving. It covers most North American major mainstream car makes. It is the first data set that includes reverse engineering black box OEM signals of LKA systems. And we're leveraging VLM. It provides rich scene annotations and semantic information, which is also new to in the literature in the LKA context. Okay, so now let's jump into the second part. So with those granular LKA data, so we can wait to evaluate the real world LKA's performance. It is the first large-scale empirical study of the real-world LKA performance, and we are with those reverse engineering CAN data, so we are able to diagnose LKA failures and classify them into perception, planning, control, and quantifying their performance on challenging geometry such as the curves. We also developed some physics guidelines to illuminate geometry design for LKA technology, and we also share a machine learning model for transportation agencies to help them to assess their road readiness for LKA and to help them understand if this road segment is ready for the current LKA technology and where and how they can improve their road infrastructure. So it follows a very simple pipeline. We will start with defining the evaluation metric, and then we evaluate the performance of LKA under normal conditions and challenging conditions. So the performance metric is quite simple. So we are looking at how much the vehicle deviates from the center of the road. So here, what we call the lane deviation. So these figures illustrates the concept of lane deviation. And here we show an example of what we get from the CAN message. So this is an image from the dash camera, and on the right, it shows the lane line detection results from we get from the CAN bus. Through reverse engineering, we know what actually they mean. They have 4 values, which means non-detection and high confidence detection and low confidence detection and high confidence with for dashed line. Let's first look at the error case performance in normal conditions. Here, by saying normal conditions, we refer to good lane marking, straight draw geometry, normal weather conditions, and normal and good lighting conditions. And the finding is that from this distribution, the finding that we find is that LK centers within the lane very rare in clear driving conditions, and the standard deviation is quite low. It's almost is about 0.1 meter, which is actually significantly smaller than human driving. So here we find that LK performs very well in normal conditions. So technology behaves well in desired conditions, and it behaves better than human drivers. It stays within the center and try to center the vehicle pretty well with very small errors. And of course, we know LK can have a lot of issues in challenging conditions, and that's a focus of this evaluation. So to assist that, we extracted a small data set out of the whole OpenLKA data set. We call it OpenLKA failure data set. So we went through the whole data set and extract all the failure cases. And how we find the failure cases, we identify those segments where the lane deviation is greater than 0.0 meters, or the lane keeping system actually disengages abruptly during the LK operation. For each failure incident, we get the before-after conditions, and we extract a 6.5-second video to cover that failure incident scenario. We also get the corresponding CAN data and the area VOM annotations. So to check out these data sets in our GitHub, OpenLKA GitHub, we have a sample there. So the structure is that we have different, each car has a folder, and each failure incident, as shown here, it is a 6.5 second video with reversed CAN messages and the VOM annotations. And to give you a sense of how many failure conditions we have collected, so here are the numbers. And as you can see, we have different numbers of LK failures from different car makes. So that's probably due to the uneven data distribution from our target experiments from the community drivers. But when we conduct the data analysis, we do sample equally from different car makes. And this is the example of the 6.5 second for each LKA failure incident, where any of these two conditions were triggered. Now we try to diagnose those LK failures. So here's an example. We try to understand what happens in this case. So why in this driving scenario, the lane detection suddenly fails. So it is a case where in Tampa you have strong bright sunlight and you have white pavement. So then it creates very low contrast between lane markings. So here you can barely see, actually we have white lane markings. and the white concrete pavement, it creates very low visual contrast. So at this point, we can find the lane detection signals. It drops from very good detection to non-detection, and we can confirm in this scenario, it is a perception failure that causes the problem here. To gain more insights of where or which lane line or which part of the road creates the issue, so we need more help. So those CAN bus, either vehicle internal data only records failure or not, but it does not tell you the code. It does not explain why. And as mentioned earlier, OEM only ships those black box technology. It never shares the details of the algorithms. So to understand where exactly the road causes the LKA detection failure, we need some approximation. So here we use LANet, so which is a baseline lane detection algorithms on the market. So we believe even if those technologies, black boxes from OEMs, they're not open sourced, so they are most likely use similar technologies developed in the literature. So which is can be a variation of LANet. So here we use LANet, and we send those LKA failure images to LANet, and LANet would identify where exactly the lane markings are missing. Like here, it tells us the lane markings are missing in this region, and we can see those are the tire marks that interfere with the road lane markings detection. So with the help of a LANet, such a proxy of this black box system, it helps us to understand more, help us to conjecture which part of the road, which part of either is wet conditions or lane markings actually create or may contribute to the failure of lane detection of the black box systems. Other common cases in lane line detections failures include heavy rain and lane line transition, failure lane line, and here we all provide very solid ground truth evidence here. So this is a CAN signal where it fails, and this is a corresponding road image the dash cam video captured. So note that all those detection failures happened on the real LKA systems in real cars. So that's the state of the practice. Okay, so other than perception errors, we've also found that lane keeping assistance system is not smart enough like human drivers. A good example is that when the road is suddenly split into two, such as there is a highway diverge in the off-ramp, so LKA is often confused and evidenced by those large lane deviations or an LKA disengagement. And on curves, so LKA is not as smart or as flexible as human drivers. So human drivers often do corner apexing on curves for safer and smoother trajectories, but LKA seems to adopt very rigid rule where it still tries to stay right in the middle of the curve. So that is not safe, that is not comfortable, and which has to be rectified. And we found that LKA does not learn defensive driving skills of human drivers. To give you one example, when you see an upcoming truck on the opposite lane, what human drivers would do is to lean to the right of the road to create more space. So this flexible and defensive driving skills has not been found in LKA technologies. So even if we have very smart systems technology, even if we have large language models here. We have some reasoning models here. We do not have, we haven't seen any like defensive driving skills in LK system in today's technology. Okay, so I think I don't have too much time left. I will go 5 minutes more, then we enter Q&A. So this is an example of control challenge. So this is to say that even if the detection and planning is correct, sometimes in challenging curves, the vehicle's steering capability is not enough. Here we show the desired and the actual lateral acceleration. So even the model outputs the correct desired acceleration, the vehicle might not catch up with that. So that means that control system can provide enough lateral acceleration to execute the planning. So we come to the summary of common LKA failure modes. You have faded lane lines, occlusion, low contrast between pavement and lane lines. And for lighting, it has some glaring, insufficient light. And for geometry, it has lane line transition, sharp curves, and of course, it can be a combination of those conditions. To give you a more statistic overview, so all those LK challenging conditions were annotated, were labeled by VOM and manually checked by students in the group, and we get the statistical summary here. And in terms of the faded lane line and pavement lane line contrast are the two most dominant single features that correlate with the LK failures. And speaking of combinations, we see faded lane line plus insufficient light is the most dominant combination contributing factors to LK failures. Yeah, so for geometry design, we find some very interesting finding. We find the LK failures. We find the lane deviations tend to grow linearly with the road curvature. And all the data are collected from the real driving scenarios. So based on those findings, we also came up with some practical implications, such as the geometry design. So mathematically, if you have a torque limit, or if you have the limit of the rate of the torque, it can be translated into the road radius and the transition curve, the length of transition curve. Those are all very important metrics in road geometry design. And to assist transportation infrastructure, so we know not everyone can get the same device on the road. So most likely those transportation infrastructure, they only have a table which records what their lane marking conditions are, what their road conditions are. So it is fine. So we can translate those tables to our VOM annotations, and we have trained some random forest models and XGBoost models for those transporting agencies, for them to check if their road infrastructure is ready for LKA technology to predict if LKA will fail on their segment. Okay, so I will give a very quick summary of the third work. So LKA fails the law, and it is very hard for human driver to oversight the black box. So what we can do? So the idea is that we can alert human drivers. We can predict the failures 2 or 3 seconds before it happens. Then we send the alert to human driver, or we warn the human drivers the LK is going to fail, and try to give human drivers more warning and more request attention to prevent crashes due to the lack of oversight. And based on the LKA failure dataset, and this is the desired scenario we want to have. So we want VLM to read the road, to understand the road scene. And before this LK deviation, like LK failure would happen, and we train the model that is smart enough to alert us that 2 or 3 seconds before. Then the human driver is able to know we need to be prepared to take over control to prevent lane departure. So that is the idea of the third work, and we use the same OpenLKA failure dataset, and we train a VLM to achieve that. This is the structure of that model. Technically, we use LoRa, which tries to improve the training efficiency of the fine-tuning VLM. And we found that the trained model is able to provide very good prediction of the potential LK failure, actually with 70% accuracy. And more importantly, it also provides a reasoning of why it thinks your current LK is going to fail based on a single dashcam video. Yeah, well, so if you're very interested in this part of the work, I strongly recommend to check out the archive papers I shared at the very beginning. And due to the time limitation, so I will summarize the work here. So we produced the first data set specifically designed to predict LK failure, containing raw 10 data from production vehicles, rich annotations from dashcam videos. And this LK alert, it achieved nearly 70% accuracy on the alert, alerting the potential LK failure. And we achieved that by fine-tuning a small 7D model using LoRa. And we demonstrate the feasibility of segmentation tasking, guiding those VLM models to learn the failure reasons of these black box systems. Okay, thank you for your time. I'll be happy to take any questions you might have.
Okay, thank you, Dr. Zhou, for the wonderful presentation. I can see it is very clear and a very comprehensive dataset was built up. It has considered many scenarios, especially the extreme conditions such as heavy rain. Does the audience has any questions or would you want to discuss? You can just unmute your microphone and ask questions. You can just unmute your microphone to ask questions to Dr. Zhou. Actually, I have a question. I'm not so familiar with the transportation. And the LK actually it is very popular for the modern vehicles, such as especially the electric vehicles. And many vehicles are embedded with the LKA. And for different countries' origins, it is the traffic habit. It is different, such as for UK and Hong Kong region, they are right-hand traffic countries and origins. And for the United States and mainland China, they are left-hand traffic countries. Different countries' origins may have different driving habits. Can this influence the LKA performance or not? I'm curious.
That is very interesting question. Thank you for bringing that up. I think regarding centering the car within the lane, it's probably the same. It doesn't matter if you right steer or left steer. But speaking of the challenges LK would encounter, I believe those right steered vehicles and the road design definitely would have an impact. Since I talked of some cases where the lane line transition is basically the change of lane widths or change of lane lines. So since the LKA has not seen enough data in their training process, so it does not know how to do or what to do in those corner cases. And personally, I'm not sure if the right steer roads can be corner cases for LK. I'll be happy to test them out since if I can get the chance. Yeah, so that's a very good question. Probably I should go back and take a look at the community data set to see if someone is from a right steered country. So then I would be able to look at to answer the question in a better way. Yeah, that's very interesting. Thanks.
Okay. And I saw that it is a guiding model was trained with the dataset. Was this model installed in the vehicle, or it is a model installed in the cloud?
So yes, the answer is that we install this model in the NVIDIA AI Edge box. So it's an NVIDIA Orin. So we actually embedded that guiding VLM model. We put it into a small AI Edge box. So we want this model to run as a alert, as a driving alert assistant, so alongside the LK system. So it can warn us a potential LK failure to help us to better oversight the system. And to answer the question, yes. And currently we're trying to improve the efficiency, the time efficiency of that model. So currently it runs at 2 Hertz. So basically it's 0.5 seconds give you an alert or not. But it's not very ideal. So compared to LK system, it runs at 20 Hertz. But our alert system runs at 2 Hertz. So we definitely want to improve the efficiency of our alert system. And with AI development, it becomes more and more possible since we are able to use smaller and smaller model. So we can distill our current model and try to use them on even lighter weight models that would probably increase the efficiency of this model. Yeah, hopefully in one day we can run that on our phone or in a phone, Android phone-like device that does not have any GPU to run this alert system.
Yeah, we can have lighter models, and also actually the performance of the course are actually improved.
Yeah.
Okay. Since the time is very limited, if you have any more questions, you can just ask Dr. Zhou by email, and we are also looking forward to hearing more seminars from Dr. Zhou in the future. And
thank you.
Okay.
Appreciate it.
Okay.
Thank you, guys.
Okay. We may end the seminar. Thank you all.
Thank you, Dr. Thank you for your attention. Have a good day.
Thank you.
Bye-bye.
Bye-bye.